In section 9.5, we are going to look at the ratio, the root, and the comparison tests. The ratio and the root test are similar. Each requires you to calculate a specific limit characterized by either R or P, where in the ratio test we are making a ratio of a term and its previous term and finding the limit of that ratio as k goes to infinity. For the root test, what we're doing is we're taking the kth root of our expression, forming our infinite series, and we're looking at what happens when the limit for that goes to, or what the limit is as k goes to infinity. So basically each of these two tests have a different calculation, one R and one P, but the conclusions are the same. So we know that the series is going to converge if either R or P is 0 to 1, including 0, not including 1. We know that it's going to diverge if it's greater than 1, anything greater than 1, and if it's exactly equal to 1, either R or P, then our test is going to be inconclusive. So let's look at an example of each one. So in our first example, we have the infinite series k e to the negative k from 1 to infinity. We are going to use the ratio test here. And as you go through, you're definitely going to be able to make some pretty easy determinations about whether the root test is a good way to go. You can certainly try to use the root test on any problem, but anytime you have a power of k and you take the kth root, that power of k is going to be eliminated. So you want to sort of look for that in terms of convenience in a problem. Now here I do have a k power, but it's in the denominator, so I'm not sure how convenient that is, and for that reason I chose the ratio test instead. So if I look at my term a to the k plus 1, I'm going to be plugging k plus 1 into my expression. And if I look at a sub k, I'm just going to get the original. And what I want to do is I want to find the limit as k approaches infinity of the ratio of those two expressions. So I'm writing a ratio or a fraction between each of those two. Now, it's often helpful to go ahead and combine or simplify before you take your limit. So what you'll see is that you do have two terms that have the exact same base. And so let me sort of pull that out and look at that separately. And if I distribute that negative, it also might help. But remember, when you're dividing exponential terms that have the same base, the rule is that you take the top exponent and you subtract the bottom exponent. So let's see what we get when we do negative k minus 1 minus a negative k. Well, that's the same thing as negative k minus 1 plus k, so that our k's actually cancel out, leaving us with e to the negative 1. So in terms of simplifying, what I really have is e to the negative 1 times k plus 1 over k, and because e is to the negative 1 power, I'm just going to bring it downstairs. So let's let k go to infinity, and as we do, we're going to notice a ratio of infinity over infinity, which implies that L'Hopital's rule can be used. Taking the derivative of the top, I'm going to get 1, and taking the derivative of the bottom, I'm going to get e. So 1 over e is my limit. The question that we have to ask ourselves is, based on the three possibilities, does that mean that our series is convergent, divergent, or we're still not sure because we have an inconclusive test? So what we want to look at is 1 over e between 0 and 1? Is it greater than 1? What do we get? So 1 over e is like having 1 over 2.7, and 1 over e is less than 1. And so because of that fact, because it's less than 1, because it's between 0 and 1, then we can say that our series, our infinite series, is convergent. Okay, so it falls into this category right up here. Let's do another example. This time let's look at the root test. And I'm going to pick something that's really convenient for using the root test. And what we're going to work with is k over k plus 1, all raised to the 2k squared powered. So notice I have a power of k, and if I were to take the kth root of that, it's going to decrease that power, which is really nice. So let's first of all calculate p. Okay, so p is going to be the limit as k approaches infinity of the kth root of this expression. There's a lot of simplifying I want to do here before I even begin to take the limit. First of all, remember that the kth root is equivalent to the 1 over k power. So I can raise this whole thing to that 1 over k power, and when I do, my powers are multiplied. So think about what happens when you take 2k squared and multiply it by 1 over k. It's going to leave you with just a 2k. So in calculating my p, I'm actually finding the limit as k approaches infinity of k over k plus 1 to the 2k power. Okay, so here's where things get a little bit challenging with this example, because what I end up with is really inside my parentheses. If I were to let k go to infinity, I'd have 1, and then in my exponent I'd have infinity. So I get this indeterminate form of 1 to the infinity, and so I have to use that e to the l, taking the natural log property, in order to continue to evaluate this limit in order to find p. So what I'm going to do is I'm going to take the natural log of the expression, the natural log of this whole expression here, which is going to allow me to take 2k and move it out to the front. So I'm going to have 2k times the natural log of k over k plus 1. And at this point, if I were to let k go to infinity, I'd have infinity times 0, which is still indeterminate. So I'm going to continue writing this one more time, or rewriting it I should say, in order to put it into a L'Hopital form. I'm going to put 1 over 2k as the denominator, and that is equivalent to multiplying by 2k. And so now what I have is 0 over 0 in that L'Hopital form. Okay, let's continue and use L'Hopital's rule to find this limit. So I've got the limit as k approaches infinity of this natural log of a quotient, which I can break up into a subtraction, properties of logs here. It's just going to be easier when I use L'Hopital's rule and take my derivative. Taking the derivative of each term on the top separately, the derivative of the natural log of k is obviously going to be 1 over k, and the derivative here is going to be 1 over k plus 1. In the denominator, I've got 1 over 2k, and its derivative is going to be negative 1 over 2k squared. Let's clean this up. Let's get a common denominator in the numerator. So a common denominator is going to be k times k plus 1. That'll give me k plus 1 minus k over that common denominator. And then instead of dividing by this fraction, let's multiply by the reciprocal. You can see that the k's cancel, k and negative k, so that gives me positive 1. And then also this k is going to cancel with one of those k's. So in my numerator, I'm left with negative 2k, and in my denominator, I'm left with k plus 1. Now we can actually evaluate the limit, which is, again, in L'Hopital form, infinity over infinity. So taking the derivative of the top and the derivative of the bottom gives me a limit of negative 2. So the question is, p equaling negative 2. What kind of conclusion can we make at this point about our series from that value? And so what we know, I'm sorry, that's not true. That's not true either. We forgot that we had taken the natural log in the beginning, so we need to use that e to the L to rewrite it. That's a really easy thing to forget. I do it all the time, so hopefully you can just continuously remind yourself to not do that. So, my apologies. The p-value is 1 over e squared. That's what we want to use to determine whether it's convergent or divergent. So, how does that compare to 1? Well, that is less than 1, which means that the series converges. Just like in the last problem, we go back to our rules here, and if it's in between 0 and 1, then our series converges. And that's what we have.